In this lecture, we look at the remainder theorem. An application of the division algorithm of polynomials focuses on the significance of the remainder in long division. Here's an example. Suppose you have this fourth degree polynomial, and you divide it by x minus 2, and you get 2x cubed plus x squared plus 2x plus 9, and a remainder of minus 18. Then if I ask, what is f of 2, you could plug in 2 for x, and get that expression in red, times x minus 2 is 2 minus 2 in blue, minus 18. If I take the expression I have, the equation above, and plug in 2, I get this expression in red, blue, and black. Ignore that expression in red, however complicated that is, because it's multiplied by 2 minus 2 in blue, which is 0. And anything times 0 is 0, so everything cancels out except the minus 18. So if you plug in 2, in this case, you get minus 18, which is the remainder when you divide by x minus 2. If, by the division algorithm, we divide a polynomial by some divisor, d of x, and we obtain a quotient q and a remainder r, so that f is equal to q times d plus r, then if c is a 0 of the divisor d, if c makes the divisor d equal to 0, then f of c is q of c times 0 plus the remainder of c, and that's just the remainder at c. The divisor set equal to 0 simplifies, and you focus on the remainder. This is especially important if the divisor polynomial is nice and linear, something like x minus c. Suppose we divide a polynomial by x minus c, obtain a quotient q of x, and a remainder r. Then I can write it this way. My function f of x is the quotient times x minus c plus r. And so if I plug in c for x, then f of c is the quotient at c times c minus c plus r. C minus c is 0. All you have left is r. The remainder theorem says if f of x is a polynomial, then f of c is simply the remainder you get when you divide the polynomial by x minus c. Let's do some examples. Here's a polynomial of degree 100. Suppose this polynomial x to the 100th minus 3x to the 98th and so on is divided by x minus 2, gives some messy quotient of degree 99, I won't write it down, and a remainder of 55. Just take my word for it. I've done the computation using the computer algebra system at Wolfram Alpha. Given this information, what is f of 2 and why? Well, if we write my polynomial f of x as x minus 2 times some quotient q, which happens to be degree 99, and I haven't written it down for you, plus a remainder of 55, then if we evaluate this expression at x equals 2, when we plug the 2 in, we get 0 times this messy q plus 55, and that's just 55. So f of 2 is just 55. The messy quotient is unimportant here. Another idea, suppose I have a polynomial of degree 999, and when I divide it by x squared minus 9, I get a quotient and a remainder 4x plus 11. What happens when you plug in 3 to this polynomial? This polynomial f of x of degree 999 is not shown, neither is its quotient, and we don't care. They're not important. If I write f of x as x squared minus 9 times some unknown quotient plus this remainder 4x plus 11, then when I plug in 3 for x, I get 3 squared minus 9 in front times the quotient at 3 plus 4 times 3 plus 11, but 3 squared minus 9 is 0, so I have 0 times that quotient, plus 12 plus 11, which is 23, so my answer is 23. If I can write my polynomial out in terms of the divisor, quotient, and remainder, if I can make the divisor go away, all that remains is the remainder. The remainder theorem helps motivate a shorthand notation for dividing a polynomial by a nice linear factor of the form x minus c. This shorthand notation is called synthetic division, and it will be the subject of our next presentation.